Okay, so in the last lecture video, I have talked about the convolutional encoding. And now in this lecture video, I'm going to give the lecture based on the state diagram and the trellis diagram. Okay, so let's start with the state diagram. So state diagram is nothing but a simple representation of the encoder that we have seen earlier. So throughout this state diagram, we can encode our message signal. So one thing that you have to remember is that this state diagram, it is a generalized diagram for any particular message. That means, suppose if I have a message bit 101, this state diagram, it is not dependent on this message only. So this state diagram, it is a particular diagram for a vector connection or vector diagram. So in the previous lecture, I have told you that there are some vector diagram G1 and G2, which was 111 and there was 101 like this. So for this specific vector diagram, we are drawing this state diagram. And for any kind of message bit, we can, if I use this message bit or any kind of message bit here, we can use this and find the code word sequences from here. So we can say that this state diagram, it is not for a particular message. So it is for a particular connection vector. Okay. So now let's get into details of this state diagram. So here you can see there are boxes like A equal to 0, 0, 1, 0, 0, 1, and 1, 1. So the thing is that in this state diagram, these boxes, these are nothing but the possible contents of the rightmost k-1 stages of the register. So you can see that we know that there are shift registers that we require in the previous class, and the number of shift registers were k into k. So in our previous example, the small k was 1 and large k was capital K was 3. So total number of shift register we required was 3, right? Now the rightmost k-1 bit, that means k-1 is equal to 2. So the rightmost 2 bit, it will be the possible number of states in this case. So in this case, as we have 3 shift register and k-1 gives us 2, so the rightmost 2 bit, it will be our state. So for this 2 bit state, how many combination will be there? So you know there can be 4 combination possible: 0, 0, 0, 1, 1, 0, and 1, 1. And we are just giving this 4 combination as a name as A, B, C, and D. So let me first draw the things. So we are giving state A as 0, 0. Then comes our state B, which we are taking as 1, 0. Then state C, which is 0, 1. And state D, which is 1, 1. So these are the 4 possible state combination that we are talking about. So these are the states. Now, from the vector diagram, we'll see that, or for the shift register, we'll see that there are 3 possible shift register for that example. And for that possible shift register, we are starting with this A equal to 0, 0. That means from here, we are starting with this 0, 0 combination from A. Now, there are only 1 bit left at the left hand side. So for this 1 bit left, what we can say that in this case, either there can be 1 here or there can be 0 here. So there are 2 possible combinations remaining for this position only. So either they can be 1 and they can be 0. Okay, so before that, I would like to say one thing is that in this case, if I use the solid line, then it will represent the input bit 0. And for the dashed line, it will represent the input bit 1. Okay, so you have to remember this thing. That means solid line will represent the input bit 0 and dashed line will represent the input bit 1. Okay. So now we'll use this thing for different kind of combination. Like we have the present state 0, 0. That means we are talking about this state. And for getting the next state or the future state, you can either have 0 here or either have 1 here. So now if I consider that the first case, where if I take the value 0 here, then what happened? Our present state is 0, 0. Our present state is 0, 0. And now if I take the 0 as the left side bit, then what will happen? The future state, it will also become 0, 0. That means the thing we are showing here, from the state 0, 0, it will remain at 0, 0. And this is occurring due to the input that we are giving here as 0. So as I've already told, if the input bit is given as 0, then we'll represent it by a solid line, right? So we are just representing it as solid line, and it is back to its original position. That means the present state is 0, 0, and after inserting input bit 0, it is again becoming 0, 0. So it is again becoming 0, 0 and coming back to its position. And just we are just giving the output here 0, 0. That means from this 0, 0, we are again getting 0, 0 for the future state for our input bit 0. And this 0, 0, what does it represent? So it represents for our connection vector, like our connection vector was like this. So there was a modulo 2 adder connected, and in this case, they are connected like this. So what would be our code word for the first case? As 0, 0 will give us 0, and in this case, it will give us also 0. So this 0, 0, it represents the output of our code word. So this is our first case. So now considering this point, we are giving 0 here. Now instead of 0, if I insert 1 now, what will be the future state? So the previous state is already shown here as 0, 0. Now after inserting 1, the future state will be 1, 0. That means it will go from 0, 0 to 1, 0. Now what will be the line here? So as you know, if the input bit is 1, then it will follow the dashed line. That means you have to give the dashed line. So from 0, 0, it is becoming 1, 0, and we have to give the dashed line here. So from 0, 0, it is going to 1, 0 with a dashed line. That means we are considering our input bit as 1. And what will be the output now? The output will be here for 1, 0, 0. If I modulo 2 add here, then it will be 1. And for this case, 1, 0, 0, it will also be 1. That's why we are giving 1, 1 as our output. Now the state 0, 0 is finished. Now after that, we are going to evaluate for the state B, which is 1, 0. Now if we are in state B, that means if we have 1 and 0 here in the present state, again there can be two combinations, either for 0 and either for 1. So if I take 0 first, then our present state is 1, 0, and our next state is 0, 1. That means from 1, 0, it will move to 0, 1. That means there will be a line like this. And as the input bit is 0, that means we will have a solid line. So there will be a solid line like this. So let me draw it with a green line. So there will be a solid line because we are giving the input bit 0, and also we are going to 0, 1 because our present state is 1, 0, and after inserting 0, we are going to 0, 1 position. And again, instead of 0, if I just give the value 1 here, then from 1, 0 position, it will go to 1, 1. But the thing is that now, as we have inserted 1, we have to give the dashed line, because for the dashed line we have said that the input bit will be 1. So from 1 0 it will go to 1 1 with a dashed line. And what will be the output in this case? In this case, for the first case, 1 plus 1, it will be 1 plus 1 will be 0. 1 plus 1 will be 0, and for 1 plus 0 it will be 1. So in this case the output will be 0 1. And also for this 1 0 to 0 1, the output will be 1 0. Okay, so we have finished for state A and state B. Now let's go for state D. So in state D we have the input 1 1. That means present state is 1 1. So now if I insert 0, then it will move from state 1 1 to 0 1. That means from 1 1 to 0 1, and it will be a solid line. And what will be our output? Our output will be 0 here and 1 here. That means output will be 0 and 1. And again, if I insert 1, now from 1 1 it will again go back to 1 1 in the future state. So 1 1 it is again getting back to its original 1 1, and in this case the output will be 1 plus 1 equal to 0 and 0 plus 1 equal to 1. So in this case it will be 1, and for the second case it will be 0. So the output will be 1 0. So now we have finished this D state. Now for the next state, which is our C state, our present state is 0 1, right? So we have 0 1 here. And if I insert 0 first, then from 0 1 it will go to the future state as 0 0. So from 0 1 it will go to the 0 0 with a dashed line. And in this case the output will, in the both case, it will be 1 1, right? 1 1. So output will be 1 1. And again, if I have 0 here, instead of 0, if I give 1 here, then the state will change from 0 1 to 1 0. That means from 0 1 to, it will go to sorry, in the previous case, for 0 input it should have a solid line instead of dashed line. So it should have a solid line. And now for input 1 we are having a dashed line. So it will move from 0 1 to 1 0. 0 1 to 1 0. And the output in this case will be 0 here and also 0 here. So 0 0. So this is the whole representation of the state diagram that I have shown here. So it is shown also in this state diagram that is represented here. So what is the benefit of this state diagram? So what is the purpose of doing it? So I have already told you that this state diagram, it is not for a particular message bit. So it is for a particular connection diagram. So for a fixed connection diagram that I have showed here, we are getting this type of vector state diagram. Now, if I want to find the code word from a message bit, let's say we have a message bit m equal to 11011. So this is our message bit, and we want to encode this message bit to our code word sequence u. So what will be our code word? So we can find the code word easily from the state diagram. Then what we will do, we'll start with a bit message bit 1. So for 1, what will happen? For 1, what will happen? It will follow the dashed line first, right? So if I follow from, we'll start from the 0 0 position, and from for 1 input bit 1, what we'll do, we'll follow the dashed line first. So if we follow the dashed line first, this is our followed line. So now for this following line, what is our output? 1 1. So we'll write 1 1 here. Again, the second input bit is 1, right? Then again we have to follow the dashed line, right? So now we are at B state, and now if I follow again the dashed line, then what will have to move? We have to move from this position to this position following the dashed line, and the output bit will be 0 1. So we are just writing the 0 1. Then comes 0 input. So for the 0 input, we have to follow the solid line, right? So here from D position, okay, so I may have a mistake done there, so it should be dotted line. Okay, so for from D position, if I follow the solid line, then it will go to this position and the output will be 0 1. And again for 1, we'll follow the dashed line, which is this one. That means output will be 0 0. And again for the last one, we have to follow the dashed line, right? So this was our dashed line. Now we are in this state, and if I follow the dashed line, then our output will be 0 1 again. So 0 1. So this is our code word sequence for our particular message bit M, which is 11011. So by this way, from a given message bit, we can find a code word sequence very easily. So this is the purpose of state diagram, from where we can find various amount of code word from our message signal. So there can be various combination of the vector diagram, and for that combination, you have to draw the state diagram, and it's very much important for your lab quizzes and also for your theory quizzes. I hope you have understood this part. Now, if I go to the next diagram, which is the Trellis diagram. So this is called the Trellis diagram. So the Trellis diagram is look like this. So here you can see that there are a bunch of dots given and also the connection shown here. So if I have to draw this Trellis diagram, first of all, we have to identify how many states are there. So as you can see, for our previous example, we have 4 states. So for the 4 states, we'll give 4 dots. So at first, I'm just giving the dots here. So first dot, second dot, 4 dot. And each dot, they are representing each state. That means first state, A equal to 0 0, then 1 0, C equal to 0 1, and D equal to 1 1. So this is our 4 states that we are talking about. And in this way, for time t6, we have to draw all the dots like this. Okay, so these dots, they are nothing but the same state shown. That means this first row of these dots, they represent nothing but the same state, A equal to 0 0. Similarly, for the second row, they represent the state 1 0, and same goes for the state C and state D. Now, if I start from the beginning, so from our state diagram, you will see this is our state diagram that we have already drawn in the previous page or slide. So you can see, if we are now at position 0 0, that means at starting. Okay, let me first write one thing, that our solid line that represents 0 and the dashed line, it is representing 1 here. Okay, so solid line representing 0 and dashed line, it is representing 1 in this case. So now, if we start from this 0 0 position, that means in this state. Okay, so before that, this Trellis diagram, it is also same as the state diagram in that manner that this is only for a certain vector diagram or vector connection. It is not for a particular message bit that we are talking about. Okay, so If I start with a equal to 0, 0 position, that means in this position at time t equal to t1, then from this position, if I give the input 0, 0, that means if our first bit that we have changed, it is 0, then it will follow a solid line and the output will get as 0, 0, right? That I have told you in the previous slide. So for a solid line, that means for a 0 input, we are getting an output of 0, 0, and it is coming back to its original state. That means 0, 0, it is coming back to again 0, 0. That's why we are just writing a line here from 0, 0 state to 0, 0 at time t1 to t2. And again, for our one input bit, from 0, 0, it will move to 1, 0, right? And in this case, it will be a dashed line. So we can draw like this. From 0, 0, it will move to 1, 0, but in this case, it will be a dashed line. And output associated with it is 1, 1. So I'm just writing it at 1, 1. Okay. So this thing, we are just doing it from step A to step B. Now, from this B state, now we are in this B state. So now from the B state, if I give the input, 1, then what will happen? It will be a dashed line and it will go to 1, 1, right? That means from this B position, if I give one input, then it will go from 1, 0 to 1, 1. So it is going from 1, 0 to 1, 1 following a dashed line. And in this case, the output bit is 0, 1. So we are just writing here 0, 1. And another thing is that if I use 0 as an input bit, it will follow this line. That means a solid line, and it will go from 1, 0 to 0, 1. So from B position, as we are giving input bit 0, it will go from 1, 0 to 0, 1. That means 1, 0 to 0, 1 in this position, and the output will be 1, 0. So this is at time t equal to 0, and the rest of the case, what it does follow, it will follow the same thing, like from 0, 0 to, it will remain at 0, 0. So for this point, and again it will 0, 0, 0, 0 for the whole position. And same goes for also this case also. So from here, it will follow the dotted line. There will be also a dotted line like this, and also there will be dotted line like this. And for the 1, it will be from this position to this position. Okay, so this is our time t3, and okay, it will be from here to here. Okay. So now at time t3, our A state and B state is completed, right? Now the C state and D state, we haven't completed that yet. So what will be this C state and D state? Now for C state, that is for this position, if I give the input as 0, then it will follow the solid line and it will go to 0, 0, right? That means from 0, 0, it is going to, for 0, 1, it is going to 0, 0, and it is a solid line. So for 0, 1, it is going to 0, 0 following a solid line. And the output is 1, 1 in this case. So similar thing will happen for all the 3 cases. And again, for the dashed input, what it will follow from 0, 1 to 1, 0. So from 0, 1, we are at position 0, 1, it will 0, 1, 2, it will follow to 1, 0. 1. And now again for the D state, so if I give the input 1, then it will again go back to its original 1 position. That means if I have state 1 1 for the dashed input, that means 1, it is just remaining in its 1 position, and the output associated with it is 1 0. And also for the zero input, it is going from 1 1 to 0 1. So for the zero input, it is going from 1 1 to 0 1. And the outputs associated with it is 0 1. Okay, so this is the trellis diagram that I have drawn here, and this is the diagram. This is sign T4, T5, T6, and 0 0 0 0 0 0 0. Okay, so in this way you have to draw the trellis diagram first, and this is for a particular connection diagram that I have told you, that G1 is 1 1 1 and G2 is 1 0 1. For this connection diagram, where you will find this trellis diagram. So now, what purpose is this trellis diagram serve ours? So the thing is that similar thing. So if I have the message bit like m equal to 11011, then what will be our code word? We can find through this trellis diagram. But how? So let's say if we are having this one first, LSB. So for this one, we'll have what? We'll follow the so for this one, we'll follow the dashed line first, right? So you can just check here. So if I follow this line, the dashed line, then the output code word associated with it is 1 1. So I'm just writing 1 1. Then for second one, we'll again follow the dashed line. That means there are two lines here, a solid and dashed. We'll follow just this line. And associated output with this line is 0 1. So we are giving 0 1. And for the third input message bit, which is 0, we'll now follow the what? We'll follow the solid line. So here you can see there are dashed line and solid line here, but we will follow the solid line. Our output corresponding to it is 0 1. So 0 1 will be our output. And for 1, we'll follow again the dashed line, right? So we'll follow this line, which is associated with 0 0. And last one, what will happen? We will follow the dashed line again, which is this line. That means the code word is 0 1. So the thing is that from our message bit that we are having here, by trellis diagram, we can simply find the encoded version of our coded sequence easily from if I can draw this type of trellis diagram. So this is a one kind of way we can find the output through our trellis diagram. And there is another thing. So this trellis diagram, through this trellis diagram, we can also decode the signal. So how we can decode the input and the output? After sending a signal due to some noises or any kind of disturbance, the input bit that I have sent, they can be changed at the output bit. Okay. So we have to successfully decode the message signal from the input bit that we try to send, and get out the original message signal that is sent from the input side, right, or the sender side. And we have to get the original signal successfully at the output side or the receiver side. So this thing, it can also done by the trellis diagram, that means the decoding thing. So this decoding is called the Viterbi decoding. So to understand this Viterbi decoding, what we have to do first, we have to know, we have to follow some steps. Like if I have an input message signal or sequence like this 11011, then the transmitted code word that after encoding, the code word that we are sending is 1101010001. But after sending the transmitting code word, the receive sequence, that means at the receiver side, the sequence that we get is like this. And you can see that there is one mistake at the output. That means there is 100 becomes 10 at the receive sequence. And this is the error sequence that we are talking about. So how to decode this? That this in this point we have a error message. So this message or this way we are going to see here how to decode the thing using Trellis diagram. Okay, so before doing that, just see this that we have a term called like Hamming distance. Okay, so if I have 1 in a message bit and if I get 0 so the Hamming distance is 2. That means there are 2 bit changes. That's why the Hamming distance should be 2. And if I have 10 and if our original message 100, then what is the Hamming distance? The Hamming distance is 1 here because the 1 bit has only changed. If I have message like 01 and we get 01, then the Hamming distance is 0. That means there is no changes in the message bit. So now this is the Trellis diagram that we have already drawn. Now here you can see in the states, instead of giving the output or writing the output in this path, they have written 2011 like this. So these are nothing but the Hamming distance. How they have written it? So this is our 00 in the Trellis diagram, and in the transmitted code word we are having 11. That means the message that we have transmitted is actual message is 11. So between, if I compare this 00 and 11, the Hamming distance is 2. That's why they have written 2 here. And for this branch, you see the code word is 11, but the transmitted code word is also 11. That means they are same, right? So for this, the Hamming distance will be 0. That's why they have written in this branch 0. Same goes for this path also. For 00, we are just sending from T2 to T3 in this state. The value output code word is 00, but the transmitted code word is 01. That means there is 1 bit change. So we can say that the Hamming distance is 1 here. So in this way, in this decoder Trellis diagram, we just replaced all the code word with their Hamming distances like this way, 0, 1, 2. In this way, we have just replaced all the code word with their Hamming distances. I guess if you see this by yourself, then you will understand how they are represented and what is the difference. Like if in this case, if this is our 10 code word and our sending message is also 01, that means there is a 2-bit change. 1 becomes 0 and 0 become 1. That's why we are getting a Hamming distance of 2. So in this way, all the Hamming distances are represented here. Okay. So after representing all the Hamming distances, now what we have to do, we have to find the distances of the state matrices which has the shortest possible path. Like this is our state matrices that is shown here. That means from T1 to T2, how much Hamming distances it has covered. So that is represented by these state matrices. So tau A, it is 2 here because the Hamming distance between T1 to T2 is 2. So this is the state after the time T2. Okay. So for this case, it is 0 because the Hamming distance between these two is 0. So this is after the time T2. Now for after the time T3, the state matrices will be like this. That means for first state, the Hamming distances or the paths are like 2 plus 1, which is written here 3. And for B state, it is 2 plus 1, which is 3 also. And for the third state, it is 0 plus 2, which is 2. And for the fourth state, it is 0 plus 0, which is 0 here. So this up to this, I think there is no problem because each of these points, they have only one state, one line coming. Okay. But now from T3 to T4, you can see Previously there are only one path and one path, but now for these points you will see we have two different paths coming, right? So for this case, this one and this one, these two paths, and for this B state, this one and this one, there are two paths are there. There are two paths like this. So now if I calculate the state matrix from T to T3 to T4, you will see for the state 1 there will be 2 plus 1 plus 1, that means 4. And for this path, what is our state matrix? 2 plus 1, that means 3. So as I've already told you that we have to take the minimum or the shortest possible path state matrix. That's why instead of taking this line, we'll just take the red line and discard the first line. Okay, so here in the state matrix you will see they have discarded the first line and they have chosen the line that had the shortest possible of state matrices, which is 3. Okay, so similar goes for the next line also. So for the next line you will see there are two paths, possible paths coming to this point. So at the first line, it has the state matrix 2 plus 1, 3 plus 1, 4. And again, for the second line, it has 0 plus 2, 2 and plus 1, 3. So which one is smaller? This 3 obviously. That means this line, first line, it will be discarded. So you can see the lines they have discarded, and only this line is remaining with a state matrix of 3. So similar goes for other two lines also. So among these 2 points, they have taken the line that has the shortest amount of Hamming distance. That means this line. And also for the last one, this is the shortest possible distance, which has a 2. So in this way, the state matrices, we are taking the shortest possible path and discarding the others, which has highest amount of Hamming distances. And for transition from T4 to T5, we'll see there are only one possible state in this case, and they are shown like this and no problems in this case, just drawing it after that. And for the last case from T5 to T6, see again the similar thing is happening. There are two states in this case, and among these two states, what we are taking, we are just taking the states which has lowest amount of path. So for these two paths, the lowest path that we get is for this one, for this path, and which is 2. And we have also written this. And other parts for these two, we are having this path is very low amount, and other two have this path and this path, which gives us the lowest amount of Hamming distance. So now, why we are doing this? Why we are taking this lowest amount of shortest possible path here? The thing is that if our message bit is like 101, and if our code word is, let's say, a random code word like this, okay. So now, if this is our encoding code word, at the output or at the receiving side, what we will get? We get exactly this type of output or the receiving messages at the receiving side, right? We should have found this type of code word. But the thing is that if there is some kind of noise or in some kind of disturbances, these values of 0, 1 bit they can be changed there. So if there is no noise, then we will get the exact same messages that we have transmitted from our transmitter side. But if this case happens, if there is no noise, then what will be the Hamming distance between our transmitted message and the message that we have receiving? So the Hamming distance must be 0 in all the cases, right? So the total amount of state matrices, if there is no noise, should have been 0, because there should not be any changes at the output code word. There will be no error. But the thing is that as there are noise there and also there's some disturbances, the input bits or the sending bits, they just get changed. And that's why we get some of the changes in the output bits. Let's say this 1 0, it becomes 1 1 at the receiver side. That means there is a 1-bit error here. And for this 1-bit error, the distances that we are talking about, it will be changed, right? There will be some distance. Instead of 0, we'll get 1 or 2, some values, because now the transmitted message, they have changed from our original messages. So the shortest possible path, we are looking for it, because the shortest possible path, it means that the message signal that we are sending, it will be exactly same to the receiving signal. That means there is no noise there. But whenever we'll get some amount of changes, then there will be some 1 or 2 Hamming distances at the receiving side we'll get. So in this example, you will see the shortest this possible amount of distance that we get is 1, right? And you will see all the paths from T1 to T2, T2 to T2, the message bit that we have sent, they have 0, except this position, right? That means this T4 to T5, we are having a 1. That means in this case, there must be a error. That's why the Hamming distance that we are getting is not 0 here, that's 1. So if I go back to the previous slide, from previous slide here, that you can see that in the receiving sequence for T4 to T5, the transmitted code order is 0 0, and we are having 1 0 here. That means that in the receive sequence, the message bit has changed, right? And that's why instead of 0 0 in this position at the code word, we are having 0 1. And also in the Hamming distances, we are having 1 instead of getting 0. By this, we can say that there is an error signal in this message bit from T4 to T5. So this is the process by which we can find any kind of error in the message. That means how many bits are there with error signals, we can find it throughout this Viterbi decoding algorithm. So this state diagram, Viterbi decoding algorithm, and also convolutional encoding, they will be discussed details in your theory classes also. But for this, what you have to do before coming to the next lab, that means your experiment number 3, you have to thoroughly understand these things. That means how these things work, because this is the prerequisite to understand the simulation part of your experiment number 3. I hope you will all try to go through the video lectures and try to understand the things. And if we have any problem, we will discuss it in the physical classes. Okay. Thank you, everyone. Assalamu alaikum.